Good morning. Welcome to Krishna's classroom. Let us continue with our exploration of the concept of connectedness. So let us briefly recall what connectedness was as we have defined in our earlier talks. So X is a metric space. Let X be the union of two separated A and B. Then X is not connected. Because clearly then X is connected if there does not exist such a representation. So what you have is this. To elaborate on this point, we say that we have A and B are non-empty. And you have X equal to A union B. And we have A intersection B closure is empty. A closure intersection B is. So if A and B are such that these two conditions are, or these conditions are satisfied, then you say A and B are separated. So if X is expressed as the union of two separated sets, then, or can be expressed as the union of two separated sets, then X is not connected, and X is connected if such a breakup is not possible. Okay, so that's the one that we had been working with. We now explore the properties of these sets or the space altogether, assuming it is connected. Okay. So the first theorem in this context is the following. And this is a characterization theorem. We prove that X is connected if and only if, this is a characterization, if and only if the only, put it this way, okay, put it this way, if and only if the only subsets which are both open and closed are so X is connected if and only if the only subsets of X which are both open and closed are X and phi. That means, see, in any set or in any metric space X is both open and closed. So also the empty set is both open and closed. And what it says is that there is no other subset of X which has the property that it is both open and closed. And this property essentially characterizes a connected set. So let us prove this theorem. Very simple result. As usual, we assume the second statement is true. So assume the second statement is not true. That is, there exists a proper subset A of X which is both open and closed. So what we are assuming is that there exists a proper subset A contained in X with the property that is both open and closed. So that means we are negating the second statement. Then claim X is not connected. Okay. So the implication is that it's a contrapositive one. X is closed, X is connected. Implies there exists no proper subset So this is the implication of that. This is, of course, as we have proved many results already. You want to prove A implies B, then this is equivalent to proving not B implies. So we take up this route. Okay. So this is the strategy. Okay. So we have assumed the negation of the second part of the statement. So we have specifically assumed that there exists a subset, a proper subset of X which is both open and closed. Okay. Now what we want to say is that X is not connected, which means, so claim, so what we have claimed already. So we have to show that A, B to proper subsets. X that means saying A and B are connected such that A, B are separated and so we start with, so define B equal to A complement or X slash A. That is A complement. Okay. Now we have the property that so this is the definition of. Then of course you have now we have to show that these sets are separated. That means we want to show that these conditions are satisfied. These conditions are satisfied. That is A intersection B closure is empty and A closure intersection B is. Now what is given? Our assumption is that A is both open and closed. Therefore, A open implies B is closed. And B A closed implies B is open. Therefore, both A and B are closed and open. Therefore, let us now you see. Therefore, A equal to A closure, B equal to B closure. Now we know that A intersection B is empty because B is the complement of A. Now that is A intersection B closure is E. Similarly, A closure intersection B is, therefore now X is equal to lies so if there exists a non-trivial subset of X which is both closed and open, then we are able to split X as the union of two sets, two disjoint sets A and B, with the property that they are separated. Therefore, X is not. So that's the first part of it. Now we prove the next assertion. The next assertion is that so what have we proved? So what is the conclusion? The conclusion is that if X is connected, hence the conclusion is that, which further implies both open and closed are so one part we have, okay, and now we prove the converse. Okay, so we prove the converse. That is the proof of this. So once again we resort to a similar argument. We shall assume that X is not connected. This implies there exists proper subsets A and B of X such that A is A union B into X, A intersection empty, and A union A intersection B closure is empty, and A closure intersection B is empty. Now this statement is then redundant. Okay. These two implies. So we want to claim that considering the A that we have obtained here. Now we claim that open and okay. So what we have is this. We have A intersection B closure, which in turn implies A complement union B closure complement. All of it. Okay. Now B closure is closed, which implies B closure complement is open, which implies A closure is closed, sorry, A complement is closed. If A complement is closed, then A is open. A complement is closed, which implies A is open. So A is open. And what is the consequence of that? Okay, similarly, So A is open, B is open, but B is equal to A complement, which implies A complement similarly B is so we have both A and B closed and open because this is enough. That is A is both closed and open. Or this is at this stage I can stop it. I have to talk about this. Although it is possible to prove it. And this in turn implies the only subsets of which are both open and closed are X and 5 implies okay, so that completes the proof. So this in turn gives us another definition of connectedness. So what is that definition? So let us put it across. Say that X is connected if there exists a such that A is both okay. Good. X is connect the only subsets of X which are both closed and open. Are so that is the new definition of connectivity. Okay. Now we give a second possibility of characterization, another characterization of connected sets. Another characterization. Another characterization of connectedness. So we have the following. A topological space A is connected if and only if every continuous function every continuous function to the 2-point set +1 and -1 is a constant. A constant. That means either it maps x to +1, the entire x to +1, or it maps x to +1. This is the theorem, and this is an if and only if condition, and trying to find out what you call connectedness through the help of a continuous mapping. We have, in this context, I think it is interesting to observe that we have already proved that a continuous function from x to y, where x and y are two metric spaces, maps a connected metric space to a subset of y which is connected. So this is what we have. Continuous functions. map connected sets to connected sets. That means connectedness property is retained by continuous fs. Means if x and y are two metric spaces, and if x is connected and f is a map from x to y, then if f is continuous, then it follows that fx, f of capital X, that is the image of x under f in y, is also a connected set. So this you read in the along with this one. Okay. So let us prove this. Okay. Suppose is a continuous but non-constant function. Then f is onto, because it is non-constant, it takes both the values +1 and -1 at some points. Therefore, this is on. Okay. Now define A equal to f inverse of and B equal to -1. That means this is equal to -1. Empty. Because if you have a common point for A and B, then it is mapped to both +1 and -1. which is not possible because f is a function. That's obvious. It's trivial. Now, clearly, a is a non-constant function implies non-empty and b is both are wrong. Both a and b are now you also see that a is closed because f inverse of 1, and this is a closed subset of so also it is open since minus 1. Of course, in both these cases, we use the continuity of f is mixed. And therefore, what you have is that a is both closed and as well as open. Okay, so it implies x is not so what is the consequence? And again a contrapositive statement. Make a contrapositive statement. The contrapositive statement is that only continuous function every continuous function from f from x to is a constant function. That's the one that we have. Now we prove the converse implication. Now assume, so to prove that assume again we are resorting to contrapositive argument. So what we prove is the following. Claim there exists every plus or minus 1 is which is not a constant. That is the negation of the second statement. So let us prove this. So we prove this. So X is not connected there exists non-empty both A and B, open and closed, such that and of course and A intersection B So these properties are satisfied. Now let us construct a function. Now define right f of x equal to 1 x belonging to and equal to minus 1 whenever x belongs to. Now this is well defined. Because now we claim that f is continuous. Let me prove it as follows. Okay. Then x belongs to A or x belongs to, without loss of generality, assume x belongs to. Similar argument you can use if you take x belonging to. Okay. Let xn the sequence xn converges to x. Now A is open. Therefore, there exists R positive such that Bx are contained in it, which implies xn belongs to Bxr for every n greater than n r, for some n r, because of the convergence. What does it mean? So if you look at f of xn, see f of xn by definition is maybe plus 1 or minus 1 depending on where xn belongs to. At least we can say that f of xn equal to plus 1 for every n greater than r. Okay, because Bxr is a subset of K. That means, see, this is the situation. A is closed, sorry, A is open. So if you have an x here, there is a whole neighborhood. So if this is the point x, then see, if you have a sequence xn that converges to x, maybe the first few terms may be in B, but certainly at some stage onwards, xn enters the Bxr. So consequently, f of xn is equal to plus 1. What does this mean? Okay, so fxn converges to x. F is continuous. So therefore f is continuous on x being arbitrary. Similarly, f is continuous therefore f is continuous non-constant on x. Okay. So we have proved the existence of a continuous function which is non-constant on x. Right. So that means that is if f is continuous, by contrapositive argument, inference, we have f is the only continuous function f continuous from and f is constant connected. So that's the second characterization here of connectedness. So I think that's a place where we can stop today. Thank you very much.